Hi, and welcome to another video of Stat 420. In this video, we're going to talk about making predictions from our linear model, as well as introducing measuring the variance of our model by measuring the residual variance. So making predictions from our model is pretty straightforward. So we're just going to take an x value, plug it into the equation, and see what we would predict y to be at that x point. So let's take a look at the context that we've already seen before, and that is going to be trying to estimate the stopping distance of a vehicle based on the speed that vehicle is going. So we have an equation, we have a best fit line that we have kind of modeled for that relationship using the least squares method. And so we'd like to calculate the estimated stopping distance of a car traveling 15 miles per hour. So what we're going to do here is plug in y hat equals negative 17.58 plus 3.93 times 15 miles per hour. And so we can calculate that. I need to grab my calculator right over here because I didn't grab it ahead of time. And so I'm just going to plug that in, and we're going to have negative 17.58 plus 3.93 times 15, and I get out 41.37. And so in this case, our y variable stopping distance is measured in feet, so that means that we would estimate that the stopping distance would be 41.37 feet. Now, I'll also mention that this data actually comes from a very old data set. I think it was from somewhere in the earlier mid-20th century. So I should mention that these values that we're going to find are going to be maybe a little bit strange. I'm sure for 15 miles per hour, the stopping distance would probably be a lot shorter now. Maybe not a whole lot shorter, but maybe a little bit shorter. But just kind of some context there with this data. So we can make predictions from our linear equation for really any value that we plug in, except when we're working with values that might fall outside the range of collected data. So it's important to think about interpolation versus extrapolation when we're making predictions from our linear equation. So interpolation would be the safe thing to do. So this is safe. It would be predicting y based on an x value within the range of x values that we have collected. So let's say that we've collected data from between 10 and 30 miles per hour. Then it's safe for me to use this equation for an x value within that range. However, extrapolation is when I'm trying to predict y based on an x value outside of the range that we've collected for x. So if I was trying to plug in and estimate a stopping distance when x is less than 10 or when x is greater than 30, then I'm not so sure what the relationship looks like. And that's because maybe we've observed a linear relationship or whatever relationship we've defined here in this particular range, but we don't actually know what happens once we leave that range. The relationship might change form. It may no longer be linear. And in fact, if you think about it, like when we're looking into the negative x range, the relationship might be completely different or non-existent. So we always want to be very, very careful to make extrapolations from a model just because we don't actually know what happens. We're making a lot of assumptions when we do that. So extrapolation is, I'm just going to say not safe. I won't say that we should never extrapolate. It's not that this is just always wrong, but it's something that we have to do very cautiously. All right. So residuals is something we've already talked about before, but that's just going to be the error in our model at a particular data point. So just because we're making a prediction from our model doesn't mean that that value is actually going to be the case. And that's because there's still going to be variability in the data, that our particular predictor is not the only thing that accounts for this response. So we might kind of think of a model as being response equals prediction plus error or something like that, or sometimes you hear it, response equals signal plus error. And that's just kind of pointing to the fact that we have some predictive power, but not full predictive power. So we have some kind of advantage, we have some reduction of variability in our estimate, but there's still going to be some unexplained variability. There's still going to be some error in our prediction. And so we usually use the letter E, or epsilon would be kind of the parameter error that we might use to talk about this unexplained part, the error in our model. And so that's just going to be the actual data point that we have minus our prediction from the line. That would be our residual. So again, I think we've seen it before, but a residual is just going to be that vertical distance from the line. Some residuals are going to be negative, some are going to be positive. So this right here would be an example of a negative residual. This and this would be examples of positive residuals because they're above the predicted point for that particular point. But residuals is something that we just have to be aware of. And residuals also help us kind of estimate how much error we have in our model. So we can estimate the variance in our model by completing this calculation. This is going to be, you might call it the standard deviation of our residuals or the standard deviation of our errors, which if you want to think of the E is standing for errors there. And that's going to be kind of the sum of the squared residuals, and then we just divide it by almost n. It's going to be n minus 2, but it's some value close to n to kind of turn that into some sort of average. So sigma squared we might think of as the parameter representing the variation in our model. So there exists a parameter, there exists an amount of variance in our model predictions. And then we can use our data to estimate that with the sample variance for the residuals. One thing that we won't get into a lot of detail here is just going to be why we're dividing by n minus 2 and not dividing by something like n. So if we were dividing by n right here, then this would truly be the average squared residual, right? But the fact that we're dividing by n minus 2 has to do with the fact that this is otherwise going to be what's called a biased statistic, which we'll talk about in a later chapter. But kind of the short answer for now is a biased statistic is when we're making an estimate of something, but we're going to consistently underestimate it or we're going to consistently overestimate it, rather than kind of rather than knowing that our estimate should be centered around the true parameter. So for example, a sample mean is an unbiased estimate of a population mean. However, a sample standard deviation is not an unbiased estimate of the population standard deviation, and that has to do with the fact that we're using a sample statistic in the calculation. So that's what we're doing here. We have beta hat naught, we have beta hat 1. Those are sample statistics. Those have error in themselves. And by doing that, we're going to introduce some error into the estimator, and it's actually going to end up being a biased estimator unless we correct it in the denominator. But we'll talk about that again in a later chapter. Just know that dividing by n minus 2 versus n just has to do with making this an unbiased estimator rather than a biased estimator.